Hello, in this video I'm going to talk a little bit about complex numbers. So the first thing of which that must be established is, talking about what is a complex number. So let's say that we consider the following equation. X squared plus 1 equals to 0. Now, if we try to solve this equation, then basically we have x squared plus 1 equals to 0, but then you get x squared equals to negative 1. Now, basically the next step that you would need to do is essentially just take the square root on both sides. But the only problem is that we end up with this issue where it's just a matter of, well, how do you find the square root of a negative number? Mostly because this number right here is not real. Well, if it's not real, then in that case, it's probably imaginary. So from here, the thing of which that we normally will say is that, well, let's say, for example, that let's say that, for example, that if we were going to try to solve this, then we can actually say, by definition, that if we let, let's say, like, by letting, so here's what we'll do. We'll just say that negative 1 is equal to I squared, or I squared equals to negative 1. So in this sense, we have that our equation is actually x squared equals to I squared, which in this case, if we take the square root on both sides, this is where we get that essentially by taking the square root, you end up with that x is equal to just I. But what was I? I was the square root of negative 1. So in this case, we have that the square root of negative 1, so we have that the square root of this is going to be negative I, comma, I. Okay, so in this sense, like, we have our solutions, but make no mistake, these are actually not real numbers. Now, in general, you have that a complex number is of the form, let's say that, okay, so we'll just say that a complex number is of the form, okay, so it's of the form, we'll just do it like this, a plus bi. Now, in this sense, you have that there's two components. So you have that there's a real, and then you have that there's an imaginary. Now, whenever you talk about, for example, when A is 0, when B is 0, and so on, you do end up with different cases of numbers, like like a real number, pure imaginary, and so on. I don't want to really go that much too in depth to it because you have the textbook and you can always just take a look at the different types. My goal is mostly that you just want to be able to apply some type of operations with this because that's typically what we need. And also, like, let's go ahead and just put z. Okay, so z is a complex number. Now, in this sense, let's see. Let's go ahead and just practice looking at some square roots. So like, for example, let's say that you had 8 plus the square root of negative 25, and this is divided by 10. Now, accordingly, you have that, okay, so essentially you have that, that's a negative value. So one way that you can kind of approach this problem is to kind of think of it this way. If you have the square root of negative a constant, basically that's going to be the square root of the constant times I. Normally you put the I in front of the radical, for instance. So if a is a perfect square, you can actually write that out. So we have that this will be 8 plus, okay, so we have the square root of 25, and then we have an I, and this is divided by 10. But notice this. If we split it up, so we have 8 over 10 plus, now the square root of 25 will be divided by 10. So in this case, we have an I right there. So that's going to be 4 over 5 plus 5 over 10. And this is going to be I. Now, basically, furthermore, we have that that's going to be 4/5 plus 1/2, and then we have an I. So this is our complex number that we ended up with when we combined, or yeah, when we kind of simplified it, for instance. Now, one thing that's kind of interesting is that when you work with complex numbers, for example, um, you have that it doesn't work exactly the way that you think it does. Because, for instance, if I was to take negative root 36 and I'm to take this by negative root 36, so negative 36. So if I want to solve this, then normally I might actually say, for example, that, okay, well, I was taught that same exponent and then it just multiplies. So in that case, you have like kind of like, let's see, right, so you have the square root of 36 squared, which gives us 36. Well, that's not totally true, because mostly this only works, that old property where you have same exponents, you have that only works for real numbers, but this is not a real number. So in any case, you have the square root of negative 36 multiplied by negative 36, and that equals to, by definition, well, you have by definition, the first one is 6i. But then you have 6i again, and that equals to 6i squared. But what is I squared? It's negative 1. So you have negative 6. So you can kind of see how basically applying the definition is very important in this sense. Let's do one more. Now, let's say, for example, that you had the square root of negative 48, and this was divided by the square root of negative 8. Okay, now by definition, you have that you cannot technically say that that's the square root of negative 48 divided by negative 8, and then from there just say, oh, okay, well, that's just the square root of 6. But that's not true. So what we can do is actually just go ahead and do it in steps. So for example, I know that the square root of negative 48 is the same thing as the square root of 48 times I. Now, even if this does work out, like to say, for example, like root 6, then that's probably like an anomaly. So we can go ahead and say that we have, okay, so let's say that we have root negative 8. So yeah, even though this will be probably the same thing, we still have to go through the process. So this is going to be square root of 8 and then times I. Now we can see that the real or the unreal, the i's, they cancel out. From here, you'll notice that you end up with the square root of 48 divided by the square root of 8. However, we know that that's the square root of 6 multiplied by the square root of 8, all divided by the square root of 8. So then it actually gives us it gave us the answer that we thought it was going to give us, but consider this, that only worked out because the imaginary units canceled out. So in that sense, we weren't allowed to use this method specifically because it only works for real numbers. So it's not going to always work out this way. And you can kind of see that with different examples, for instance. Now, you do have that when we work with complex numbers, like for example, if you want to solve x squared plus 6x plus 13 equals to 0. Well, in this case, we have that we can actually solve this by using the quadratic formula. Now, the quadratic formula says basically that let's do it like this, x equals to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, where a cannot be equal to 0. So in this sense, we have basically everything that we need. We have a is equal to 1, b is equal to 6, and c is equal to 13. So let's see. Okay, so x equals to negative 6 plus or minus the square root of 13 squared minus 4 times 1 times 13. Actually, it's 36, right? So yeah, it should be 6 squared. Okay. And that's 13. Okay. And then all of this is divided by 2 times 1. So you have 2 times 1. Now, from here, you have negative 6 plus or minus 36 minus 52. And all of this is divided by 2. Now, 36 minus 52 is basically negative 16. So you have that this will be negative 6 plus or minus negative 16 divided by 2. But in this case, you have that that's going to be negative 3 plus or minus, okay, so you have that that's going to be 4i, but basically you have that it's divided by 2, so it's going to be 2i. So essentially you have that the solutions are as follows. You have negative 3 plus 2i, comma, negative 3 minus 2i. And these are the solution set. Note that basically you have that for quadratics, that you're always going to have a plus and a minus for your solution set. Basically, those represent conjugates of each other. So basically, like for example, if you have something like z equals a plus or b I, then basically a conjugate is a representation as so, where you have that that's going to be a minus bi. So it's essentially just the opposite in value, or in sign, sorry. Now, the thing of which that, we're going to look at as we kind of do this small review of complex numbers is considering what can we do with them. Well, what you can do with them is almost the same as real numbers. So essentially you have that when you add and when you subtract, basically you have that if you take a complex number like a plus bi and you're going to add it to c plus di, Well, essentially you have that the reals combine themselves and you end up with the following. So in this case, you have that basically a complex number added to a complex number is a complex number. Well, that shouldn't be a surprise, which means that it's the same for subtraction. So, yeah. Uh, well, actually, it would be A minus C, wouldn't it? Yeah. Actually, let me just go ahead and delete this because it'll kind of get confusing if we try to combine it using PM. So I'll just do this. Okay, so essentially for subtraction, you have that if you're gonna do like A plus BI, and then you do minus and then C plus DI, basically this will be just A minus C, and then you have plus B minus D. So that's kind of why I was getting confused. So you have that these are the complex numbers that you would end up with when you add or subtract. Now I'm only going to do probably just like one example because I want to be able to look at multiplication and division, and then furthermore just look at how you can use them in trig. Technically this is a review. So you have, what if you had like 2 plus 3i, and then you had minus 5 plus 7i, and then you had um, plus 6 minus, let's see, 6 minus, let me see, yeah, so like let's just do like 6i, or minus I, so sorry. Okay, so for this one, basically like what we can do is essentially say that, well, we can break the parentheses technically and then work ourselves from left to right. So let's just do this. 2 plus 3i minus 5 minus 7i plus 6 minus I. So in this case, let's go ahead and just say that you can group the reals all together. So minus 5 plus 6, and then you have plus 3 minus 7 minus I. Not I, it's actually going to be 1. Yeah. So minus 1, and then you have I. Now, basically from here, you have that this is going to equal to 3, because you have 8 minus 5 is 3, plus, okay, so let's see, 3 minus 8 is 5. So actually, let's go ahead and do this. Let's put a minus, because it's going to be negative 5. So you have 3 minus 5i, and then that's it. So we have that a complex number added to a complex number, or even subtracted, it just becomes a complex number. Now, you can technically use the calculator in your TI-83. I think you just have to make sure that it's on the right setting. But it should be fine even if you don't put it, I think. Okay, so the other thing of which that we look at within this module is that we want to know like what happens when you multiply. So when you multiply or even divide, basically there's a process that you have to go through. So for example, if you're going to look at A plus BI, and you're going to multiply this by C plus DI, well, basically you have this very complicated formula where you have AC, so you have A times C is AC, then you have plus A DI, then you have plus BCI, and then you have minus, or let's say like we're gonna do it like this: BD I squared. But basically I squared is -1, so this essentially gives you the following: AC minus BD plus AD plus BC, and then you pop an I there. So essentially this is the formula for multiplying two complex numbers. Now, interestingly enough, if you have multiple complex numbers, then in that case it's just a process of multiplying from left to right, basically in pairs. Because, for example, I could probably write down, like, for instance, like I times 1 minus I, and then I have like 2 plus I. So in this case, I would technically have to work it out from either left to right or right to left, which means that basically you would have that the complex number would end up being negative I squared, which basically means 1, and then you have plus I, and then you have plus 2I. From there, basically, it's just a process of multiplying it again using whatever really method that you prefer. So like 2 plus I, because 1 times 2 plus I. Then you have plus 2I, and then you have plus I squared. But basically, this gives you 1 plus 3I. So essentially, you have that. You don't technically need to use the formula, but I suppose it might help if you use the formula. The other thing of which that you can talk about when it comes to multiplication is that, for instance, by definition, if I really look at a complex number like a plus bi, and I multiply this by a minus bi, well, by definition, you're going to get a squared minus abi plus abi plus, no, well, let's do it like this. So let's say minus b squared times I squared. Now, basically, you have that the two values cancels out, and you end up with a squared plus b squared. So essentially, we have that when we multiply a complex number times its conjugate, you end up with essentially a real number. So, this is like one of the only jokes that I have where I would say, when we multiply two complex numbers that are conjugates, or if we take a plus bi times a minus bi, then things get real. So we have that basically, yeah, two complex conjugates multiplied gives you a real number. So mostly you're really just using this form of foiling or distributive method and so on, or you're just using the formula. So with that basically tells you that, for instance, if you're going to multiply, or say like you're going to divide a complex number. So if I divided a complex number by c plus di, the only way for the quotient or the denominator to become real is that you multiply by the conjugate. So c minus di divided by, you know what? Let's actually just change this a little because I noticed that it would actually be very clever of me if I change that to c minus di. Because if I'm dividing by a complex number, it doesn't matter if this is negative, but in this case, I'm going to make it negative. That way, when I multiply by the complex conjugate, c plus di, in order to make the denominator real, you can basically say that with confidence that the denominator is basically the sum of the components squared. So in that case, you end up with a plus bi multiplied by c plus di, and all of this is divided by c squared plus d squared, which means that you have a formula at the top. The formula at the top says that a plus bi times c plus di is the following. So but I wonder if I can just copy this right here. Let's see. Um, okay, so I just want to copy that. Um, okay, and then that's funny that it's not letting me grab the whole thing. Like that. Yeah, there's a way to grab the whole thing and see like it missed the dot. Oops. Let's just dot it ourselves right here. Okay, dot. So this is all divided by c squared plus d squared. So I just basically constructed a new formula for dividing complex numbers. So that way it's more relatable to you because you're going to multiply by the complex conjugate anyways. Okay, so I know that's a lot of information. You can probably just pause and kind of you know, digest it a little because this is how you multiply two complex conjugates, this is how you divide, and this is how you multiply. So I have a few examples. So let's go ahead and say that we want to multiply the following. We have 1 plus 2i multiplied by 4 minus 2i. Now in this case, basically we can either use the formula or we can just do distributive method. So we have 1 times 4 minus 2i, and then we have plus 2i multiplied by 4 minus 2i. Now basically we have that this is going to be equal to 4 minus 2i plus 8i minus 4i squared. So basically we have that that's going to be positive 4, so that's going to be 8, and then you have plus 6i. So there's our complex conjugate. I'm sorry, no. There's our product. So we have our product of 8 plus 6i. Okay, so yeah. Okay, so what we can do next is let's say that we're going to multiply two complex numbers that are of the same sign. So let's say that we have 5 plus, I don't want to use that one. So let's say that we have 5 plus, let me think of a number, 3i multiplied by 5 plus 3i. Now, this is actually kind of interesting in the aspect that, well, how do you multiply these two complex numbers? Note that basically this is the complex number squared. So we have that this is going to be squared. Okay, so essentially one way that you can do this is that you can technically use the following formula: a squared plus 2ab plus b squared for whenever you have a binomial squared. However, you know, because I use distributive method, it's all the same. So basically we have 5 plus 3i multiplied by 5 plus 3i, and essentially you have 5 times 5, which is 25, and then you have plus 15i, but then you also have 3i gives you 15i, and then you have plus 9i squared. Now, basically, you have that that's going to be negative 9, so that's going to be 16 plus 30i, and then that's it. So we have that, it worked out anyways because, like, even if you would have said, okay, well, that's going to be 5 squared plus 2 times 5 times 3, pop an I on there, and then you have plus 3 squared and I squared. Basically, you get the same thing because that's going to be 25 plus 30i plus 9i squared. So you get the same thing. So it's really just preference, to be honest, like whether you multiply using the formula or not. Now, normally I probably would do an example of a complex conjugate, but basically what I want to do is look at how I can divide a complex number. So let's say that you have 4 plus 3i, and then let's say that this is divided by 3 minus 4i. Okay, so in this case, we know that basically to find the complex number, we have to multiply by the complex conjugate on the top and bottom. Now, if that was a plus, this would be a minus. So you have 3 plus 4i, and then you have 3 plus 4i. Now, this is a little misleading because it looks like they're exact duplicates, but they're not, because you have that the real is 3 and the real is 4. So, it's just kind of like a little small trick. So note that basically when you multiply, you have 4 plus 3i multiplied by 3 plus 4i, and all of this is divided by, okay, so whether you're going to take 3 minus 4i multiplied by 3 plus 4i, and then you get, like 9 plus 12i minus 12i minus 16i squared. It's going to be really the same thing because essentially you get 25, right? Okay, so essentially what we can do here is just say that we are aware that the value becomes real, so it's 3 squared plus 4 squared, and then the denominator becomes 25. So let's go ahead and just get that out of the way, that we have that the denominator is 25. Okay, so we have 25. Now the next step is that basically you want to multiply through. So that's going to be equal to 12 plus 16i plus 9i. This is funny. Okay, so let's see. 4 is 12, 16 plus 9i plus 12i squared. So we get the following. Basically, we get that this is divided by 25. So essentially, we have that this is going to be 12 minus 12, all divided by 25, plus 25 divided by 25i. The reason that it's funny to me is because I got that when I divided the complex number, I got a pure imaginary number, because notice that that's going to become 0, so that cancels out entirely. So I get that that's going to be, okay, so let me just go ahead and cancel that out too. So I get that basically it's just going to leave me with 0 plus I or just I. So the answer is I. Okay, so that's kind of interesting that this one gave us a pure imaginary number. Now, the thing of which that the textbook tends to look at is, like how do you deal with high values of I? So usually in class, I go through the process of like, well, I to the 1 is just I squared is -1, I cubed is negative I, and then I to the 4th is equal to negative I squared, which is going to be basically 1. But then you have that I to the 5th power is basically just I. So essentially we have that we can either memorize this diagram or this list of powers of I, or we can actually just go ahead and tackle it by just rewriting it in terms of I squared, because I feel that nobody remembers this, to be honest, like sometimes, because, yeah, it's kind of like cyclic in this sense, and we would normally say that I has order 5, okay, because you basically get the same thing. Um, so what I'm trying to say is that, for instance, if I was to look at I to the 17, essentially what we can do here is just say, well, that's really just I to the 16 times I, and then I have that that's going to be I squared raised to the 8th power multiplied by I, and we get -1 to the 8th times I, which -1 to the 8th is +1, so that's going to be just equal to I. Well, that was actually very simple in the sense that we just did it like in steps. So the other is, for example, like what if you had um, what if you had like I to the 25? Well, in this case, if you have I to the 25, basically you could probably do the exact same thing. You could probably say, for example, that you have, let's see, I to the 24 times I, and then you have basically this gives you um, yeah, this gives you I to the 2nd to the 12th power, and this is times I. So that gives you -1 again to the 12th times I, but basically it's just going to give you the exact same thing. It's going to give you I. Now, another way that you could have done it is, yeah, you could have said, well, I to the 5th is basically raised to the 5th power because I to the 25. But if I to the 5th is equal to I, then it gives me back I to the 5th, but I to the 5th is I. So in that case, it's the same thing, I. Okay, so that was actually very complicated in the sense that, I'm explaining it without showing it. But you can kind of work it if you want to. Now, for instance, let's say that you had I to the 18. Well, I to the 18 is basically like saying I to the 2nd to the 9th power. But I to the 2nd is -1, and to the 9th, it's actually -1. So normally, I like to show it using this method versus, if we would have said I squared, we could have said I squared. Well, we did technically. We said I squared to the is -1 and raise it to the 9th, then it's -1. But that doesn't come so clear for some. So that's why it's more like if it's odd, pull an I out. If it's even, just rewrite it in terms of I squared. But the thing though is that you're gonna have these two cases where you have -1 to the n, and then basically you have that it's gonna be +1 for when n is even, and then you have that it's going to be -1 for when n is odd. So in this case, you have kind of like just an extra little thing that you would need to know, aside to like saying, okay, well, if I had I to the um, like if I had I to the let's say like 48. Well, in this case, you could probably say, okay, well, I to the 48 is really just I squared raised to the 24, but then that's really just negative 1 to the 24, which in this case is going to be positive 1. So we have that that's going to be just positive 1. Let me actually go back over here and make sure that I don't have any that are positive ones. Okay, so yeah. All right. Now, take a moment and probably pause the video because basically what I'm going to now look at is complex numbers related to trigonometry. So essentially, whenever we look at the graph of a complex number, we have to assume that we have a set of two axes, one of which is real and the other which is not. So we have this is the imaginary, that's the imaginary, and this is the real. Now, let's say that we choose a complex number, and we'll call it z. Now, z is equal to a plus bi. So in that case, that means that right here you have a, and right there you have b. Now, the very interesting thing that I love about complex numbers in the complex plane is that I can actually form a vector from the origin to here. And then from there, I can actually drop the altitude of which that gives me this right here. Furthermore, I can actually form the angle of which that we call it theta. And then from there, we have that there's the distance from the origin to where it terminates, which is called the modulus. So here, basically, we notate the modulus by the following. We notate it by, it kind of looks like the absolute value. So the thing becomes, okay, well, how do we find the modulus? And how do we find, well, yeah, mostly it's just finding the modulus, right? So we know that this is basically A and that this is B. Now check that out. Isn't that a right triangle? Okay, well, the answer in the class would be yes, it is. It is a triangle, right triangle. So why don't we just basically say that, okay, well, it looks like this is sort of similar to the rectangular coordinates, where we say that r is equal to the square root of x squared plus y squared, and then that's it, right? So it's actually the exact same thing. You have that the modulus of z is, or the complex number, is equal to the square root of a squared plus b squared. Now, the only thing though is, how do you find the theta? Well, theta is actually just taking tangent inverse of, okay, so that's going to be tangent inverse of b over a. Now, in this case, we actually need to assume that theta is from 0 to 2 pi. Okay, now in any case, actually let's go ahead and just remove this because it's coterminal to 0, so technically we don't need that. Okay, now furthermore, what we can do is essentially just look at okay, so we have our complex number. So this complex number, algebraically, is in rectangular. That's rectangular. And yeah, I can go through the process of showing you c plus di, and then you're like, oh, okay, so the reals add and the imaginaries add, and then they have their own respective angle. I'd rather avoid that, given that you're probably going to take pre-cal anyways, and you will talk about what happens with the angles respectively. But again, if you want to add two complex numbers in the complex plane, you can. But I'd rather that you focus on, just the basics, which technically it is the basic, but it's just like extra information, to be honest. Okay, so what else can we do with this? Well, note that basically there are these rectangular coordinates that we have, A and then B, right? So why don't we just basically just say, okay, so it looks like we can say that what if we were to say relative to the angle theta, we have that that's going to be adjacent over the modulus of z. I don't want that. And then I have that sine is going to be equal to b over the modulus of z. Now, it's actually very confusing with respect to, going from rectangular to what we call polar form. If you basically use that x, this would be x and that would be r, which is basically the same thing. So if you want to essentially replace this with r, you technically can, but it gets confusing. Okay, so let's go ahead and just rewrite this. So essentially we have that the rectangular coordinate a is equal to the modulus of z times cosine of theta, and then you have that b is equal to the modulus of z times sine theta. So now that furthermore tells us that z is equal to, okay, so z was equal to a plus bi. I'll just write that again. But we have that a is represented by the modulus of z times cosine of theta plus I. Actually, let's just do this. Modulus of z, sine theta, and then you pop an I there. Now, basically from here, you have that you take out the modulus and you just say z multiplied by cosine of theta plus I times sine theta. So essentially we have that this is what we call polar form of a complex number. Now, I did mention that basically z is typically r. It's equal to r. So I'm going to probably just add in here that the modulus of z is equal to r. So basically that means that essentially the complex number in polar form is actually always just r times cosine of theta plus I sine theta. I'm just putting it here so that way it's more consistent with the textbook. But, I like to use this because in this case it tells me that I know that I need to find the sum of the squares and then take the square root of it. Okay, so you might wonder, okay, so that was a lot of information. And again, you can always just pause. So this is called trigonometric polar form of a complex number. So for example, let's say that you have a complex number like z equals to let's say well, let's say that you have like root 2 divided by 2 plus root 2 divided by 2, and then you have I. So if I wanted to change it to polar form, basically I would just need to find the modulus of z. So the modulus of z is equal to the square root of root 2 squared plus root 2 squared. And all of this would be basically, let's see, all of this would basically be the square root of 2 over 4 plus 2 over 4. But you'll notice that basically that's just going to give you the square root of 1, which is actually just 1. So we have that we have that the modulus of this complex number is just 1. So in that case, the next step is let's go ahead and find the angle. So you'll do tangent inverse of root 2 over 2 divided by root 2 over 2. And essentially, this is going to be tangent inverse of 1. But tangent inverse of 1 is pi over 4 because it's from the 4590 triangle. So from here, we actually have that, that's basically it. So we have that the complex number in polar form, we have that it went from, root 2 over 2 plus root 2 over 2I to 1 times cosine of pi over 4 plus I sine of pi over 4, which in this case you have that, you can rewrite it as cosine of pi over 4 plus I sine pi over 4. Now, the textbook actually does technically tell you that you can rewrite this as the compact form cis, because the modulus is 1 of pi 4. So it's actually understood that this is going to be the same as, go back over here, root 2 over 2 and then root 2 over 2I. Now, this is actually the unit vector of, we're not really using technically vectors, but I can say that basically this is just a scaled version of 1 plus I. Because, like, for example, if you plot the original rectangular complex number in the complex plane, you'll basically see that, you can notate, where is root 2 over 2, and then where is root 2 over 2. So basically you have that it would be like right there. So in this case, this is the projection of the complex number in our plane. So we have that that's going to be the real, and that's going to be the imaginary. Now, to the naked eye, basically you can kind of tell that that angle that sits right there, that's 45 degrees and so on. So, you can actually plot your complex numbers in the complex plane if you wanted to. Okay, so let's look at an example of going from polar form to rectangular form. So let's say that you have a complex number and we have 8 times cosine of 5 pi 6 plus I sine of 5 pi over 6. Now, basically, finding this complex number, you just basically have to find 5 pi over 6, which is in the second quadrant in the unit circle. So that would be root 3 over 2, but it would be negative. And then you have plus I, and actually that'll be 1/2. Okay, so multiplying through, you're going to get that that's going to be negative 4 root 3 plus 4, and then you just pop an I. So from there, you see that basically the complex number is as follows. Now, interestingly enough, if you were to plug this into your calculator, it would give you the exact same thing multiplied by 8. And if you want to work your way backwards, you can, which I would recommend that you do work backwards, because basically you have 16 times 3 is 48, plus 16 is 64, square root of 64 is 8. So we see that basically, it kind of works itself out. But notice that going backwards, that if you go backwards, notice that you get negative 1 over root 3. So technically, that's not going to give you the right answer because, for instance, so the problem is finished, but say, like, for example, you were going backwards. You know that you have to take tangent inverse of 4 over negative 4 root 3. So basically, this gives you the wrong answer. It tells you, let's see, yeah, it tells you that you end up with negative 1 over root 3. So it's probably going to give you, negative pi over 6. So that's going to be the theta. But notice that here, over here, you have that the value is negative, but the value is positive. So that means in the complex plane, if you were working backwards, you're going to see that basically in the complex plane, it's like somewhere over here. So you have to account for that by reflecting the value that you got by 180 degrees. So in that case, you just have to add 180 degrees to your answer, so plus pi. So that's why we have that, from the get-go, it was 5 pi over 6, not negative pi over 6. And that's because of the fact that the angle measure must always be between 0 and 2 pi or 0 and 360. Okay, so that's just like a little side note, basically, in terms of like being careful with how do you convert if you're going from rectangular to polar. Now, we can look at another example of where we have, let's say that we have, so let's say that we have 2 root 3 minus 2i. And let's say that we want to go to polar form. So going to polar form, we have to basically find the modulus. So in this case, we don't have a complex number, so let's just use r. So r is basically 2 root 3 squared plus negative 2 squared. And that's going to be, so 4 times 3 is 12, plus 4 is 16, so that's going to be just 4. So the modulus is 4, but from there we need to basically find the angle. So we'll go ahead and do tangent inverse of negative 2 over 2 root 3. Now here, this is also very different. Why? Because if you were to basically plot this in the complex plane, you would have that the vector that forms looks something like this. So in this case, you have that the angle measure must be like that. Okay, I don't want that. So I have that it must be like this, but unfortunately, it's going to give you the wrong answer. So to account for the error, you're just going to add 2 pi to it. That way, it works itself out because you have that's going to be negative pi over 6 plus, let me see. Yeah, let me just make sure that this is all correct. Pi over 6, so 1 over root 3. So, okay, so plus 2 pi, that's going to be 12, 12 pi over 6, which that gives me 11 pi over 6. Okay, so from there, we have everything that we need. So we have that this is going to be such that the complex number is going to be 4 multiplied by cosine of 11 pi over 6 plus I sine of 11 pi over 6. Now, of course, technically you could actually compact this using the cis notation. So like you could use like that, but I couldn't honestly tell you how often you're going to use that notation because mostly we mostly use a different notation. Okay, so that's how I do convert it to from polar, or I'm sorry, rectangular to polar form. But what I want to do is basically leave you, for example, leave you with looking at a different format of how you can look at the complex number. So basically something that we call Euler's formula. So Euler's formula says that basically when you have a complex number, so like let's say that you have a complex number x plus yi, essentially you have that you would find the modulus, which in this case, the modulus in this case is going to be r equals to the square root of x squared plus y squared. Then you have that you find the angle. So the angle is given by tangent inverse of y over x. Now in this case, you have that this is going to give you r. So let's just write it like this: r times cosine of theta plus I sine theta. Now Euler's formula basically says that the part that is in the parentheses is e to the theta I, which is equal to cosine theta plus I sine theta. So basically you have that complex number is r e theta I. So that's actually kind of interesting. So basically we have that again, we'll just write it just again for the sake. So z equals to r times e to the theta I. Now, in any case, for example, if you had a complex number and you wanted to multiply by a complex number, then technically you can say with confidence that what happens when you multiply two complex numbers? Well, exponents, they have to add. So basically I can actually demonstrate that with the following. So let's say that I had cosine of 3 pi over 4 plus I sine of 3 pi over 4. And then I had another bracket, and then I had cosine of pi over 4 plus I sine of pi over 4. Now, I want to basically go ahead and say that, okay, so if I was going to multiply this, then technically I can actually go through the process of saying that that's negative root 2 over 2 plus I root 2 over 2. And then I know that this is going to be root 2 over 2 plus root 2 over 2, and then you have an I. Now notice that basically we could go through the process of foiling this, but who has that time? So what we can probably do instead is just say, well, why don't we do this? According to Euler's formula, it says that you have e to the 3 pi over 4 I, and then accordingly for this one, you have that that's going to be e to the pi over 4 I, which, okay, what happens when we add? So when we add, we're going to get basically e to the, or I'm sorry, when we multiply, exponents, they add. So you have e to the 3 pi 4 I plus pi 4 I, of which basically 3/4 plus a fourth is 1. So that gives you e to the pi I. Okay, so e to the pi I is actually going to furthermore tell me that I have that the polar form of this equation is going to be cosine of pi plus I sine pi. But check this out. Basically, this tells me that that's equal to -1 plus I times 0, which is actually just -1. So this gave me the rectangular real number, or the real number -1. So that's kind of interesting because Actually, we have that our answer of e to the pi I equals to -1. Notice this. E to the pi I plus 1 is equal to 0. Okay. So we have that 0 has a new representation of e to the pi I plus 1 equals to 0. Yeah. This is actually known as the uh, most beautiful equation. Okay, so essentially we have that this is known as the most beautiful equation, or that's kind of what it's known as. So furthermore, if you wanted to, you could actually say that, okay, so you basically derived that when you multiply the arguments, they basically add. So 3 pi 4 plus pi 4 is pi. But then furthermore, you have that if you were to divide, well, what happens with exponents? They subtract. So basically, operations like multiplication means adding the arguments versus dividing means subtracting the arguments. Of course, you can look at adding two complex numbers if you want to, but it's okay, in terms of like looking at it. But I feel like this is the greatest result ever to be made by Euler's formula. Okay, so that's going to be it for the complex numbers, of which this completes the set of modules for this course. I hope that you've enjoyed watching these videos and that you've learned something and that it will help you proceeding on in your studies. Good luck and have a great day.